Hi everyone. This project is called USGS Earthquake Data API, a comprehensive Flask application. We've developed a web app using Python and Flask, integrating the USGS Earthquake API to fetch, analyze, and visualize real-time earthquake data stored in a MongoDB Atlas database. Introducing our team members alongside the roles of their project. Our team consists of Harjit Brar, who took the role of developer and business analyst, then me, Naini Singh, who took the role of data analyst and developer, and lastly Tarenjeet Kaur, who took the role of project manager. We collaborated on this project. Each member contributed to key areas such as data acquisition, API development, database integration, and visualization. Talking about the project summary, this goal of this whole project was to create an application that provides API endpoints for retrieving earthquake data, supports filtering by data range or ID, date range, and present data through interactive visualizations. It's dynamic end-to-end solution for real-time earthquake insights. Talking about data acquisition, we used the USGS website for acquiring our live data. And briefly, we went for Earthquake Data API, which provides real time data in GeoJSON format. This format is easy to work with in Python, and it also supports filtering by parameters like time range, magnitude, and location, ensuring only relevant data is retrieved. Now, talking about our database design, we chose MongoDB Atlas for as a NoSQL database, and we used Python code for acquiring earthquake data manually. And you can see that in the screenshot on the right-hand side, where we imported libraries like pandas and requests. We defined our API endpoint since USGS has its own API. We set our own parameters for querying the earthquake data, and we were able to fetch that data, which is shown on the left hand side in the output. And these are some more screenshots where we've experimented with our code in Jupyter Notebook, and also we were able to imply our learnings from the whole BDAT program about how to create a chart or any visualization using Python, and also from a data that is fetched from a live API. Now, talking about using MongoDB as our database design. MongoDB's flexible schema and document-oriented structure made it an excellent choice for handling dynamic and semi-structured data sets, even like USGS earthquake data. We used Python and MongoDB's driver PyMongo, and we were able to efficiently fetch, process, and store real-time earthquake data directly from the API. Here's a screenshot where we were able to create an account on MongoDB and make a cluster and connect the cluster with the driver as Python. And here's a code available. It is also available on our GitHub repository, which we used to fetch the earthquake data. We used pandas and PyMongo to fetch our earthquake data. And here's a screenshot after running that code successfully. We were able to store our API dataset on a cloud database. Now, talking about the batch process, since it's live data, and we were particularly excited about this part of our project to keep the database updated automatically, we implemented a batch process using API scheduler. This whole script, it fetches the latest earthquake data from USGS API every 24 hours, and it stores it in MongoDB database, and ensuring the app remains current. To confirm that, after 24 hours of making the database and storing our earthquake acquired data, we were able to see after 24 hours our dataset had significantly updated, which kind of proved our batch process automation was successful. And this was a bonus part. I was able to generate an API development using Flask, which could fetch all the records by ID and also have some filters like from an earthquake that occurred on this date to that date. And we also use Postman and CURL to cross check whether our API was successful, and it fortunately was.
Hello, I am Harjit Brar. developer of this web app, and I will now introduce you a little bit about this web app, the key features of this app, and other things explain in brief. So our web app is the application we created using Flask, integration of MongoDB Atlas to display the earthquake data fetched from the USGS earthquake API. It serves as the interface where users can view the earthquake visualizations such as scatter plots, histograms, and heat maps directly in the browser. So this app is hosted on Render and accessible through a public URL. How our web app stands out. Our app is a great example of very simple, effective tools which can create significant impact. So the batch process running every 24 hours ensures the data is always up to date. Visualizing earthquake patterns make data meaningful and actionable. It's a critical component for XYZ corporations' needs. The content is a framework which is Flask for the backend. We used dashboard, we used Plotly and JavaScript to create visualizations such as earthquake locations, scatter plot, magnitude, distributions, histogram, heat map of earthquake density. We used Render to deploy this web application. Why Render? Because it's a free tier, simple setup, and it's a reliable hosting. There are some screenshots of how we deployed the Render, this web app through Render. So deployment process, deployment diagram, pipeline diagram. First was local development was done, then set up the Flask project structure. And the Flask application is developed locally, then tested locally using Unicorn and local MongoDB instance. Data visualizations and batch processes are tested. So these are the stages. How we have done it: local development, coding and testing the Flask app, GitHub repository, code pushed to GitHub, Render deployment, Render pulls the code and deploys it, public URL access, application hosted on a publicly accessible Render URL, MongoDB Atlas database, data storage and integration with web application. It was pushed to GitHub. The project code was pushed to GitHub repository. So cloud deployment. The Render pulls the project from GitHub, and dependencies and the requirements.txt are installed in a virtual environment. The Unicorn is configured to serve the app. The app is deployed and publicly accessible via Render's URL. So live application, users can access the web application via public URL. This Flask dynamically fetches data from MongoDB Atlas and renders it in the dashboard. Leveraging WSGI because for efficient deployment. Why? WSGI is a web server gateway interface. It's a standard interface between web servers and Python web applications. It ensures that the server can handle HTTP requests and pass them to the Flask app efficiently. Why? Because Flask's built-in server is not production ready. WSGI with tools like the Unicorn provides scalability, stability, and compatibility with modern web servers like Nginx. How we used it, that is how we created a WSGI PI file to expose the Flask app instance, configured Unicorn to act as the WSGI server and serve the app in a production-ready environment, deployed the app using Render, the Unicorn as the entry point. So how we did it is, while the Flask has built-in server for development, it's not suited for production environments. WSGI provides a robust standard for serving Python applications. Here is our website. It's a front-end interface of a web application, which is built using Flask for the backend and partly JavaScript for data visualizations. It allows users to interact and view earthquake data through charts and graphs directly in web browser. The homepage, the landing page of application is accessible through the URL will provide you. Displays the visualizations, earthquake data, scatter plots, heat maps, histograms, earthquake distribution of earthquake magnitudes. It's a backend connection of our app. The website dynamically retrieves earthquake data stored in MongoDB Atlas, and data is processed server side and passed to the client for visualization. We've built interactive charts using Plotly, which allows users to hover, zoom, and interact with the graphs for better insights. Here's our earthquake dashboard. Plotly, some hosted on Render. The website is publicly accessible through URL. Here's our URL. That was about our web app.
This part of the
Thank you
slide
very
shows
much.
API endpoint, which is optional. The web app that we've created exposes an API endpoint to fetch raw earthquake data in JSON.
So in this slide, I'm going to talk about the fit gap analysis, which helps us access how well the current solution meets the business or technical requirements and where there are gaps that needs to be addressed. This analysis would identify both the fit that is working well in this application and the gaps, the area for the improvement. So for example, let's talk about the data coverage and its accuracy. The application can fetch and display real-time earthquake data from the API, but it may not cover the historical earthquake data or any data from other resources. For its visualization, the application can display the data in various formats like maps, charts, and tables, but it may not offer the advanced techniques like 3D or any interactive maps with detailed information. The application can also handle the moderate number of users and data requests, but it may not be able to handle the large number of users or any significant increase of the data volume. So in conclusion, this project demonstrates the successful integration of Flask, MongoDB Atlas, and dynamic data visualization to create an interactive and real-time earthquake data application. The application is now fully ready to offer the real-time data updates and interactive charts and location-based visualization and ensuring that the user can access. Thank you.